and will do my best to make it available on YouTube so that others can see it, or that anyone can go back to particular parts and see it if they wish later, at a later date. Okay, Craig, over to you.
All right.
Just I'm sorry, before I do that, can I also ask everyone to turn their video off for this part of the presentation, because it uses less bandwidth and has a slightly smaller footprint, and we can open it up again when we're in the Q&A. Okay, Craig, finally, fully, without taking anything back, turning it over to you. Thank you.
Okay. So let me try and get this up and running. Can you see the first slide there?
No.
No. Ah, okay. Why can you not see that? Let's try that again. What about that?
You had it working a little
while.
Yeah,
I did. I'm guessing you still can't see anything?
What we see is your screen, but it's several things. It's not just
right.
the. Is it?
We'll get there eventually. Sorry, folks.
Yeah, there's.
So you can just see my face now, right?
No, well, we can see your face on the side, and in the main part of the screen, we are viewing your screen. So there you go.
Right. So now you can see it. All right. Perfect.
Yes. Yep.
Okie dokes. So I'll get into it then. Okay. So kia ora koutou. Good evening. Thank you for inviting me along. So an old series of events led to this particular talk. It started in the COVID-19 lockdown last year when I had my parents-in-law visiting, and I was discussing the woes of the world with my mother-in-law, and my mother-in-law then said, "Oh, you need to talk to Pat Basket and she can help you write this stuff up, and maybe, you know, she's got media connections, blah, blah, blah." And then Pat, I then passed some information to Pat, and then Pat passed that information to Jack, and then Jack invited me to talk. So that's kind of the thread there. Everyone hearing me okay?
Yes. Good.
Yep, okay. So normally I would talk about soil biogeochemistry. So that's basically how bacteria interacts with soil and plants to deliver nutrients to cropping systems. And I would also probably have a bit of a focus on greenhouse gas emissions from agricultural soils and agricultural systems. But today I'm going to present information that I've been accumulating since about 2008 when I started my agricultural research journey. And 2008 also coincides with when the wheels fell off, wheels noticeably fell off the global economy and new financial shenanigans began. And it also turns out that energy has a large role to play because it underpins our economy. So everything we do in our economy requires deployment of energy. So even me sitting here at the computer, I'm using energy. So basically energy use, therefore directly and indirectly affects climate change, and it also affects a good chunk of societal problems that we're seeing around the globe today. So this talk is quite high level. It's roughly divided in two parts. Part one is going to cover some background concepts, while part two I'll touch on energy use in current agriculture and the implications for future visions of food production. I won't be covering any potential paths forward during the talk. I'm going to leave that until the discussion afterwards. And I just want to point out that this is not new information. So if you look at the quote at the bottom of this page from Odom, 1971, so that's before I was born. And as typical, it seems that nothing's been done to resolve this particular situation. And a disclaimer, these are my own views and don't necessarily reflect those of my employer. So let's get in into this. So by way of introduction, let's first get a grip on the scale of the global energy problem. So 0 by 2050. This is an aspirational target whereby economies produce 0 carbon emissions by 2050. MTO. An MTO is a unit of energy standing for millions of tons of oil equivalent. So this allows a direct comparison of energy contained within fossil fuels. So we're talking oil, gas, and coal here. 12,000 is the number of MTOs used worldwide in 2019 and 2020, and it's slowly creeping up. 38 billion. That's the number or the tons of CO2 equivalents derived from burning 12,000 MTOs worth of fossil fuels. 11,000, this is the approximate number of days between now and the 1st of January 2050. 1.1 is the number of MTOs of energy we need to shift from the fossil fuel ledger to the alternative energy ledger every day for the next 11,000 days. Sorry? 1.5, the number of nuclear power plants we need to commission every day for the next 11,000 days to achieve the 1.1 MTO per day goal. And if you don't like nuclear power, 1,500 is the number of wind turbines that we need to commission every day for the next 11,000 days, and that would require 750 square kilometers of suitable windy sites every day. 11 out of 14. This is the number of critical minerals that will be exhausted building renewable energy infrastructure under a 50% green growth scenario. And I won't dwell on the energetic and environmental cost to mine those minerals. Slim to none, the chance of swapping 12,000 MTOs worth of fossil fuel energy with alternative energy, assuming no reduction in demand. 80 to 90% is the estimated reduction in energy demand required to actually meet a 0 carbon by 2050 goal, considering all resources required. So let's take a wee pause here just to reflect on what that 80 to 90% might look like for food production. That's a pretty big reduction in energy demand that we need to meet. So basically it's time to get real. And the use of biophysical economics is one way to understand if we're getting real. And that is because biophysical economics accounts for energy flows through the economy with EROI, so energy return on investment, being a central measure of the net energy available to run civilization. So what is EROI? So this is a graph of energy return on energy invested for fossil fuels. And as you can see, it's not linear. So the dark blue is the amount of energy we get out of our energy production systems. And the light blue at the top, can you see the arrow moving across the screen? Anyone? Nope. So the light blue is the amount of energy that we need to put.
Yes, we can see it.
Oh, you can. As the amount of energy we need to put in to get that energy out. So if we whiz back to the left-hand side of the graph, so when we first started pulling oil out of the ground, we got a massive return on investment. So we put in 1 unit of energy drilling a well, and we got about 100 units of energy out. Now we're drilling deeper, we're drilling offshore, we're using new methods in technology, such as fracking, and all that requires more energy and dollars. So our energy that we get out of our energy exploration exploits is much lower now. So globally, the energy return on investment now ranges somewhere between 6 and 15. So we're putting 1 unit of energy in, and we're getting somewhere between 6 and 15 out, and that's at the point of use. So that's you driving up to the petrol station and putting the pump into your car. So that range, 6 to 15, it depends on how it's calculated and what's included. So we're close to what's known as the net energy cliff. And this cliff is where energy extraction becomes a waste of time and money, time and energy. So if you put in 1 unit of energy and you only get 1 out, it's completely pointless. There's no point in doing that. And it also is the point of time when energy acquisition becomes really expensive. If we overlay the population, so that's the green line there, we are currently still within an exponential growth phase, and we're not expected to reach our peak population until about 2060. So, and the peak population is expected to be around about 10.5 billion. So the 50% of fossil fuels that we've used so far to create our incredibly complex civilization was all the low-hanging high ROI fruit. So we didn't have to put much energy in, and we got a whole heap out. Now, with population still growing, we want to advance and expand the complexity of our society using low ROI resources. So most folks have very little comprehension of the truly staggering amount of energy that our current complex global economy requires, let alone the future expectations as our population expands. And I'll refer back to that second slide where I was talking about all those numbers. It's just a truly mind-boggling amount of energy that we use. So far I've been talking about oil. Can we run civilization on alternative energy? Theoretically, yes, but realistically, with current energy expectations, there's not a chance. Now, most of our alternative energy resources have relatively low ROI, and that's because of 4 main things. So there's upfront and ongoing energy needs. So that's for building, maintaining, expanding, and replacing the alternative energy sources that we have. There's energy requirements for new resource extraction and recycling. There's energy requirements for building overcapacity and storage to account for the intermittency. And there's energy requirements for maintaining the overcapacity and storage to account for that intermittency. And finally, we're up against physics. So the second law of thermodynamics, which is conversion losses. So if you think about an industrial process that requires heat, you're far better to take a block of coal and burn that coal rather than converting electricity to heat to then run your industrial process, because there's just too many conversion losses there. So the Achilles heel for renewables is the requirement to gather up dilute energy from vast geographical areas and concentrate it. And that's something we don't have to do for fossil fuels because nature already did that for us. If you want to know where fusion sits on this graph, it doesn't. It's currently energy negative. So we have to, the fusion reactions that we've managed to get going require more energy input than we get out. And if you want to know where geothermal lies on that graph, it lies somewhere between 1 and 9. So that's between biofuels and and nuclear, let's say. And that's because it's very dependent on geology, and it's also very dependent on the years post-construction. So the older your geothermal unit, your ERI goes up. But then you start running into constraints because you then have to. So geothermal is not really renewable as such. It's still drawing on a resource that is finite. So you start running out of heat, or your drill holes that you put down start filling up with silica deposits and things like that. So you have to drill new holes. So your ERI starts dropping again. And if you're thinking about hydrogen, then don't. And Pat's already put out a nice article about this, because hydrogen's energy storage molecule. It is not an energy source. The process of making and compressing and storing the hydrogen uses a lot of energy. So anyone who talks about hydrogen is kidding themselves. So I want to note that these are all point of use EROI figures. So when you measure EROI directly at the turbine or the solar panel, the EROI is much higher, but this is an unrealistic representation of the full net energy picture. So when you account for all the infrastructure between your wind turbine and the plug that you plug your toaster in, you lose a whole bunch of energy maintaining all that infrastructure. So your EROI for that resource actually drops off. So there's currently 0 alternative energy systems that can be rebuilt, expanded, and maintained using their own energy while simultaneously supporting actual energy demand. So basically, we still need fossil fuels. The estimated minimum EROI to maintain our current semblance of civilized society at bare bones basics is about 7. And if we go back to say Roman times, they worked within an EROI constraint of about 2 to 3. And last year I picked up a paper that was looking at dynamic modeling of hypothetical renewable energy build-outs, and that paper predicted that the EROI of our global energy system would drop from our current approximately 10 down to 3 before rising to about 5 by 2060. So 5 is less than 7. So we're talking about a society that has energy available to it that's less than bare bones basics. And don't forget from the second slide that 11 of 14 critical minerals are required for that renewable energy build out. So 11 of those 14 critical minerals become exhausted under just a 50% green growth scenario. So we're quite geologically constrained. So how does EROI relate to the economy and running civilization? So on the left-hand side here, we've got a high EROI scenario. So the red arrow is the reinvestment of energy that we need to get energy, and that's quite small. And then we have a bunch of essentials that we need to cover. So food, welfare, government, law, well, if you can call government and law essential. And we have this massive big blue arrow, which is our discretionary energy available, and that can be put into building our economic growth. It can be used for investment. It's basically what we've built our civilization on. If we shift over to the right-hand side, this is a low EROI example. So the red arrow is much bigger. So a much larger proportion of the energy that we produce has to be reinvested in order to get energy. We still have the same essentials to cover. In fact, we've got more because our population is expanding, but let's just call it the same. And our discretionary amount of energy that we have available for building our economies and investing and discretionary spending is much, much, much smaller. So a lot of the social issues that we're seeing today is actually a reflection of this high to low EROI situation. We're struggling for money to find for social welfare spending, for hospitals, for education. Everything is being squeezed tight because the amount of energy that we have available to run our civilization is going down. The net energy, I should say, that we have available is going down. So to maintain our civilization and our economy, we need to use increasing amounts of energy because of that energy reinvestment. And thus we're also increasing our emissions. And this is just to maintain the supply of energy and resources that we need. We're not actually moving anywhere. This is very much a Red Queen situation. We're running faster in order to stay still. If we look at New Zealand's economy, it's built on an EROI requirement of about 25 to 1. That's very rough. So that comes from a personal communication that I had with a chap called Solis Norton, who's down in Dunedin, who's done a little bit of thinking about this. And if you look at our energy mix, so our New Zealand's electrical energy mix is 80% renewable. However, our economy is 65% fossil fuel powered. So that's some numbers that come from Stats New Zealand. And if we wanted to replace 100% of our current fossil fuel energy use with the equivalent alternative energy output, that would result in about a 25% lower net energy availability in order to live within the EROI constraints of alternative energy, as in we still need to take some energy out of our economy to rebuild our wind turbines and to fix our hydro dams and to build new solar panels and things like that. So we're actually quite lucky in New Zealand, though, because our EROI situation is propped up by hydro. So hydroelectricity has a massive EROI. So we're only looking at about a 25% drop, but if you looked globally, you'd be talking 40–50% drop in available energy if we replaced like for like in terms of the amount of energy output. And 25% doesn't seem like a huge number, but if you think about the COVID lockdowns last year, that represented only about a 7% drop in our energy consumption. So if you multiply that by 3, imagine the implications for our economy if we suddenly had 25% less energy to play with. So at this point in the talk, I would probably touch on emissions from agriculture and the need to lower agricultural emissions, but that's always quite nuanced. So we're going to try and save some time here, and we're going to jump into talking about sustainability with respect to energy use in agriculture. So what does EROI have to do with food production? So I'm using EROI for food loosely here, as it's a little bit different than the situation of pulling fossil fuels out of the ground, but it's a useful concept though. So basically what I'm trying to ask here is how much food energy are we getting out of our food production systems versus the energy we put in? So the energy we put in, I'm talking diesel for tractors, I'm talking gas for fertilizer production, I'm talking electricity for irrigation. So if you look at this cartoon, this comes from a physicist who I believe works in California somewhere, and did a little bit of back of the envelope calculation, and he came up with some numbers about what the EROI of our current foods and past food production systems look like. So hunter-gatherers are looking pretty good. So they don't need to expend much energy in order to gain a lot of energy. So they'll go out and kill an antelope or whatever and bring it back to the tribe, and they've got a lot of time to sit around and around the campfire and tell stories and sing songs. Then we had the first agricultural revolution, and that's when we started creating villages, and we started planting grains, and our EROI dropped substantially to about 2 or 3. So we're talking probably sort of up to the end of Roman times sort of type situation here, a bit beyond that. Then we move through time and we get to what they call advanced grain agriculture. So this is probably Victorian England sort of type times, where we started applying a little bit of technology, and we'd improved genetics and things like that. And that type of agriculture could support about 2 billion people. And then we had the third agricultural revolution, which is also known as the Green Revolution, where we went big time into harnessing fossil fuels. We also had some changes in other technology and genetics, and now we are, with that system, we're currently feeding 8 billion. But as you can see, the EROI has dropped below 1. So we're putting more fossil fuel energy in terms of calories than what we get out in food calories, which is not ideal. If you look at ocean fishing, 0.1. So we're putting 10 times more energy in than what we get from the fish that we're eating from ocean fishing. Aquaponics is even worse. So that's not a very good picture, really. And if we go back to our alternative energy future, if we assume that the alternative energy becomes sustainable and technology improves, and that we achieve, say, a global EROI of about 10, what happens if our food production chains have an EROI of 0.1? So that's basically means civilization falls over, because all of our net energy will go solely into food production chains. We can't do anything else. Our economies collapse. So I looked at this cartoon and I thought, well, is that really true? And I decided to try and come up with a New Zealand example. So I looked at what the rough energy return on investment for a loaf of bread in your pantry could be in New Zealand. So this graph comes from a chap called Andrew Barber, and he was looking at LCA. So LCA stands for life cycle assessment. And he's presented this graph as greenhouse gas emissions per loaf of bread. And as you can see there, for a loaf of bread in New Zealand, we produce about 1 kilogram of CO2 equivalents, which is not particularly meaningful to me.
Greg, we don't have the new slide yet.
Oh. You don't have the new slide. I don't know how to fix that.
There it is. Thank you.
You've got it?
Yes.
Okay. So where was I? So yeah, if you look at the bar there for New Zealand, it's reading greenhouse gas emissions per loaf of bread, 1 kilogram roughly of CO2 equivalents produced. And if you look at the colors there, so you've got maybe 25% of your energy is, your CO2 emissions comes from the retail and consumption. About 50% comes from storage and processing, and the other 25% roughly comes from pre-farm and farming processes, and there's a tiny wee bar there for transport. Can you see the picture of the envelope there, Jack?
Yes.
You're right. Okay, so that's my back of the envelope calculation for what the EROI for New Zealand breeders. So it is approximately 0.75. So we're putting, for a plant-based food, we are using more energy than what we get out of it. And that's based on just a standard white loaf of bread produced under New Zealand conditions. And I've removed the field greenhouse gas emissions from this equation. So I've got rid of the nitrous oxide emissions and the small amount of methane emissions that you get from producing the grain. But yeah, once you go through that storage and processing, you start getting into an energy negative situation. So the EROI at the farm gate is 2.5 approximately. And despite the sun-derived free energy subsidy that you get from that, once the grain leaves the farm, is processed in the final consumer product, you've driven to the supermarket, picked it up, taken it back home, put it in your pantry, you are now in an energy negative situation. So this leads me to think that an all-plant diet requires significant processing has major sustainability issues from an energetics perspective. If we move forward to the US food production system, and I'm assuming that slide changed. Can I get a thumbs up from Jack?
The slide has not changed.
There might be a bit of delay there.
It has for me.
Okay, whoops. And now I'm... So this is energy. So there should be a graph there that says energy use in US food production. So the US food production system is terrible. They're putting about 14, well, actually because of the declining EROI situation, it's now about 16 calories of energy that goes in for every calorie of energy that comes out. So their EROI, when you remove the food that's wasted, is less than 0.1. So again, going back to our alternative energy powered world, this is completely unsustainable and would leave no room for running anything else in our economy apart from food production. So it's not looking particularly good. So let's move on from our current food production systems and look at what our futurists are talking about with regard to future food production. So technology is our knight in shining armor. It's supposedly going to save us from population growth. It's going to aid us to cope with urbanization trends, and it's going to solve all our unsustainable agricultural problems. Now, I acknowledge that new technologies will disrupt in unforeseen ways, but we also need to acknowledge that new technology brings actual and hidden energy and resource costs that need to be considered. So we're now what's known as the fourth industrial revolution. And our friends in Silicon Valley tell us that the technology associated with the fourth industrial revolution that has applications to agriculture includes the following: new computing technologies, big data and advanced analytics, the Internet of Things, artificial intelligence and machine learning, blockchain, virtual reality and augmented reality, next generation biotechnologies and genomics, renewable energy storage solutions and communications infrastructure, autonomous and near autonomous vehicles, robotics, additive manufacturing and multi-dimensional printing, and advanced materials and nanotechnologies. Now, some of those are going to be useful, but all of those require deployment of more resources and energy. You might say, but there's new energy sources on the horizon, but I would say, yeah, maybe, but wouldn't it be better to follow the precautionary principle and assume that new energy sources are unlikely to materialize? And that way, even if new sustainable high EROI energy unicorns do arrive, we're in a far better position because of our earlier wise decisions about energy conservation. So let's jump into some examples of the EROI implications for future food production, such as urban and digital agriculture. So if we move to the urban environment first, and I'm hoping the new slide has come up for everybody, verge and backyard farming is one thing, as it still uses free energy from the sun. But given the EROI projections of future energy sources, controlled environment farms like those promoted, such as vertical farms, and if the new slide has come up on the left-hand side, there's a picture of a vertical farm. These systems don't seem particularly smart to me. Now, Singapore, for example, has a vision to locally produce 30% of their nutritional needs by 2030 using 1% of their land area. This is their so-called 30 by 30 initiative. But if you do the math, and I didn't do this, a colleague of mine did this, who was very excited by the concept of calculating this. He calculated that to produce just 1% of their vegetable requirements would require 7% of their projected annual electrical generation capacity for 2040. And in 2040, Singapore's electrical energy mix is still projected to be 90% gas-fired. So they're using an enormous amount of energy to produce just 1%. So to get to 30%, can you imagine how much energy that would produce? And most of that energy is required for suitable lighting. So basically, we're replacing the sun, which is free, with LED lights. And last year, Cornell University, so that's one of the top agricultural institutes in the world, they produced a study which labeled large-scale controlled environment agriculture in urban areas as environmentally irresponsible. And that's pretty light words, really. It's completely stupid. So new foods, algal milk, jellyfish, insect protein, the impossible burger, lab-grown fish, yeast protein. These are already things, and they're all promoted as sustainable food compared to animal farming from an environmental perspective. But what is the true EROI of the industrial scale facilities required for the production and distribution of these products? Are we simply emission swapping? Are we swapping on-farm emissions to energy-derived emissions from the factory? And what is the balance? So the IEA suggests that by 2040, 30 to 50% of our electricity is going to be coming from renewables. But those renewables still require fossil fuel input in order to aid building maintenance and recycling and peak load offsetting, etc. So we can basically assume that there will be a significant indirect fossil fuel emission from these modern protein factories. So I don't actually know the balance. I haven't done the math, but I just want you to contemplate what food production and diet choices we have. So if we take again, jump back to New Zealand and we look to the dairy industry. So there's a lot of promotion about meat and dairy replacements at the moment. Would de-intensification, better pasture and feed management, and moderation of meat and dairy consumption be better energy and resource-wise than these modern protein equivalents? And the option that I've just put up there has zero requirement for new industry. We've got the farms already. It has zero requirement for new infrastructure build, and it has zero requirement for new resource consumption. Well, apart from fertilizers and things like that. But if you compare it to producing food in a factory, to me, energetically speaking, it makes much more sense to improve what we have than to build new stuff. And also, how should we look at food? So again, taking a New Zealand dairy example, when you compare New Zealand milk from a nutritional point of view, rather than volume, our milk currently beats plant-based substitutes on almost all environmental metrics without changing anything. So our water quality is terrible because we're over-intensified. But from a nutritional point of view, when you look at that milk, actually our milk is better. So what can we do in New Zealand food production systems to improve the environmental situation and make our milk even better than better? So food production contexts are really important. So you shouldn't really believe everything that you read because there's a lot of nuance and information missing from a lot of the stories that you read, especially from an international context. So if vertical farming and new foods potentially fall over due to energy supply constraints and emission swapping, what about more conventional farms? What are the latest developments envisaged to make current farming models more efficient and sustainable? So again, I'm hoping the new slides come up. It should be a cartoon of a farm with a whole bunch of boxes around it. But basically, that picture is the top 100 companies vying to digitize farm productivity and efficiency. But my immediate question is, what energy source is going to run these digital farms? And what about the energy required for all the other resources and all the other industries required to support these companies that want to turn our farms into digital production meccas? In 2017, there was an article in The Guardian that suggested by 2025, 20% of global electrical energy would be eaten by data and data infrastructure. And a recent Nature article suggested that 20% of our electrical production would be eaten by data storage alone by 2030. So food traceability is one thing that is being promoted, and they're promoting blockchain as a way to trace food from source to consumer. So you might be aware of Bitcoin, and Bitcoin runs on blockchain calculations. Last year, the calculations required for Bitcoin used as much energy as Norway and produced as much CO2 equivalents as the London metropolitan area. So to use blockchain to trace food seems, again, a completely stupid use of energy, in my opinion. So applications such as precision agriculture could save energy because we can deliver smaller, more localized quantities of fertilizer, agrochemicals, and water. But I wonder whether the energy savings will be offset and surpassed by the energy requirements to build and maintain all the complex electronics and infrastructure enabling that precision decision making. So we could be shooting ourselves in the foot, replacing somewhat manageable methane and nitrous oxide emissions in one place on the farm with direct energy emissions from factories and building stuff, basically, to supposedly improve the efficiency of our farming systems. So this is the final slide. We have this pervasive hope that technology is going to save us from physical limits. But I struggle to see how we're going to build, run, and maintain all this new complex infrastructure truly sustainably and equitably as per the UN's Sustainable Development Goals. in an energy constrained world with a projected population of 10 to 11 billion. Food production is a fundamental part of our global civilization, and it's going to fail to deliver in the future if we do not sit back and have a bit of a rational think through the broad scale implications of this energy economy environment nexus. The idea that we can transition to alternative energy while maintaining our current level of energy consumption and produce nutritionally adequate food, even in small amounts, in controlled environments, is completely fanciful. So for agriculture, basically, I'm pushing a sensible use of resource and technology agenda here, but it makes a lot more sense to me energetically than the fourth industrial revolution agenda. So there's quite a number of ways that we can improve the energy status of the food production chains we have now. And actually a lot of those improvements can be made off farm. So that's something that I can't do. That's something an engineer has to do. And of course, this all assumes that we have a stable climate and ecosystems in which to produce food. Without that, we possibly face extinction through habitable ecosystem loss. So my take-home message basically is use resources wisely. And yeah, what decisions do we need to make today to navigate this transition ahead? And will those decisions be rationally informed with realistic expectations to keep us within the finite boundaries of our planet? And which technology applications will be beneficial with regard to actually lowering energy footprints and emissions? And I don't think a lot of the technology that's been put up will do that. And the last note that I want to put out there is to stop beating up the farmers. So agriculture is non-negotiable, and agriculture can be a big part of the solution. So we need to help our farmers and support our farmers and our growers if we're going to make a meaningful transition. So that's basically all I've got to say, Jack.
Well, I'm sure that's not all you have to say, but that's a great presentation. Thanks very much, Craig. What I'd like to invite the participants is to put your questions into the chat at the bottom of the Zoom screen. And we'll try to get through as many of those questions as we can. Craig, I'd like to start off by going back to the very beginning when you were showing us the amount of wind farms or nuclear reactors that would be required to replace fossil fuels.
Yep.
And it all assumes that we need to continue the same level of energy consumption that we're currently using.
Exactly. Yep.
And obviously that assumption is totally untenable.
Yep.
That we really need demand reduction. Do you have any suggestions about opportunities for demand reduction in our food production?
Yes. So there's there's 5 main areas that we can probably look to with regard to that. So we can save food. So we can substantially reduce the food waste that we have. So the rough calculations out there at the moment is that the amount of food that we produce today, if we were all vegetarians, would be enough to feed 14 billion people if we didn't waste any. So that's unrealistic. So let's just dial that back. Let's say that we can feed 12 billion. And we can dial that back a little bit more and we can say, okay, well, let's have a little bit of meat. And we can quite easily feed 10.5 billion people with our current production. So when the FAO says we need to expand our agriculture and we need to do this and we need to do that, that's not entirely true. One of the biggest advances we could make is just not wasting the food in the first place that we're already producing. So that would represent a huge energy saving for the future because we wouldn't be putting more of our resources into yet more agriculture. The other thing that we need to do is, well, actually, this is more from an emissions perspective, but we need to basically halt and preferably reverse land use change. So that's basically chopping down the forests in the Amazon. So we don't need to do that. We're already producing enough food. Let's preserve the lungs of the planet and don't do that. That's just silly. We can lower our emissions via the intensification of ruminant animal production in particular. So that's methane, mainly talking about there. And then we need to change our relationship with fertilizer and soil and farm management. So that's where we'll gain a little bit, especially with fertilizer. I think something like 16% of the energy that's used in agriculture goes into fertilizer production. Don't quote me on that figure. I can't remember the actual number, but it's something like that. So if we can farm with less, we save a lot of energy. And if we use our tractors less, for example, we save a lot of energy. But diesel use in our agriculture system is actually quite small. Something like if you take an LCA approach, so this life cycle assessment approach, about 4% of the emissions from agriculture are derived from fossil fuel use. Most of the emissions in a land use in a life cycle assessment come from those field emissions of methane and nitrous oxide, and nitrous oxide is coming from overuse of fertilizer.
Okay, a question about food preparation in terms of using raw foods rather than processed foods.
Yep, most definitely would save a lot of energy there. So again, that bread example that I gave, if you think about the process to get from grain through to a loaf of bread, you've got to go to the mill, you've got to grind the grain, then you've got to take that flour into the bakery, and then you've then using electricity most likely, or gas probably as well, to bake the bread. Then it's trucked out to the supermarkets. That's actually a pretty low energy use, is getting out to the supermarkets. The biggest gain would be for you to cycle to the supermarket instead of driving to the supermarket. Or some people have this idea that they need to put things in the fridge, but actually a lot of things stay quite fresh on the bench. So you can save energy by having a smaller fridge, or using your resources a little bit more wisely. Plant a garden, plant a vegetable garden.
Exactly. That's right. Zero transport cost.
Yeah.
I came across a study recently on the same theme about localizing egg production, and again eliminating all of the the storage and the processing and the refrigeration, and it was several factors, a difference in terms of the ecological footprint involved in the sort of industrial egg production that we currently have through the supermarkets. Yep. Compared to not necessarily home-based, but community-based egg production, and that's just one example again of the value of localization. Got another question here from Mark. I'll read it. It's what's your primary activity to raise awareness of those in governance who we need to support, who with support can start their journey to show up and lead and provide the kind of environmental change that's necessary? And what would help to do this?
What's my personal way of?
Yeah, what's your opinion about how to raise awareness, and especially in terms of government decision makers?
Yeah, well, that's an interesting question. So I've done a similar talk to this multiple times now to groups like this. So it's very much preaching to the choir, unfortunately. And I'm not 100% sure. Actually, this is the reason why why my mother-in-law suggested I approach Pat in the first place, because she's written some articles to at least try and get the message out there. So that's one avenue to try and raise awareness, and then maybe someone will take notice. But at this point, very few people take notice. I'm very much preaching to the choir.
Yeah. Just a personal comment. I mean, I totally agree with you. This issue of net energy analysis is simply neglected by decision makers.
Yeah, it's all about emissions, right? So
yeah. But net energy analysis is such a simple, traditional engineering methodology that it's hard to disagree with it. And yep. But they fail to do it because the assumption is simply there, well, we'll just get rid of fossil fuels and replace them with renewables, and that's all we need to do.
Yep. And you know, as we know it, that's not that easy.
No, it's incredibly more complicated because the rush to renewables is obfuscating the limitations of renewables.
Mm-hmm.
And we need to clarify what those limitations are. You know, whether it's a mineral input, the special minerals required for a lot of this technology, or the simple energy requirements. There's another question here about fusion, and if we had it, you know, would that solve anything? I have got some opinions on there, but I'm interested in
don't
yours.
believe so. So that figure of 10 comes from, an EROI of 10 comes from computer simulations of, I can't remember which group, it's somewhere in America that they've set up a fusion system, and they've used the computer to sort of make hypothetical iterative changes to that system, and the maximum power output that they predict that they could get if they could make all those iterations and changes happen is about 10. But again, well, I mean, I've been talking about agriculture, and the American food production system is at 0.1 EROI. So even if you had fusion, you are still stuck unless you improve other things in your food production system.
Yeah.
If you're replacing energy like for like energy.
Yeah, and I think it really speaks to the issue of, it's not the amount of energy that we should be thinking about. It's about how to meet our basic needs in the most efficient way possible.
Yeah.
And it's very hard to get people to think about that, because we think of progress as based on technology.
Yeah, absolutely.
I mean,
and yeah, people assume that my mobile phone here is an efficient use of energy, but in reality, the life cycle of this phone uses more energy than the entire lifespan of my refrigerator at home.
Yes.
The concept of energy and energy use is completely missing.
Yeah. I mean, I actually think it would be a bit of a disaster if we could make fusion work, because we would simply do more environmental destruction.
Yeah, exactly. Well, it's the same with mining all the other resources that we need for this renewable energy build out. It's there's already massive problems with cobalt, and already massive problems with lithium production, and socio-political problems as well that are cropping up as everyone rushes to get these resources that they need to build batteries.
Yeah. Well, there's a Spanish group that did a simulation of a 50%, a 75%, and 100% renewable energy system on a global basis. And what they determined was that the mining required for the minerals would push the greenhouse gases up above 2 or 3 degrees increase, simply because we need fossil fuels to do the mining.
Yep. Yeah.
And there's also the point that, all of the construction of these renewable systems, I mean, you've indicated how large the investment would have to be, not just in dollars, but in energy. That energy has to be on top of the energy to keep the rest of society going.
Absolutely. Yep.
And where does it come from at a time when our actual usable energy is declining?
Yeah. So that's where that, don't know if you remember the figures that I said, so that a group in I think it's the same group in Leeds, actually, they did the calculation where EROI, if we were to go down just a 50% green growth scenario, if we would drop our ERI from 10 down to 3, and then it would slowly go back to 5. So that big drop from 10 to 3 reflects both using a whole bunch of our energy to try and build all the infrastructure that we need. And then once we've got that infrastructure in place, then the ERI starts climbing again. Yeah. But it only gets to 5.
Yeah, that's right. And we really need to be making some decisions about priorities. If we're going to be reducing demand, I mean, if energy availability is going to be declining, which it is, it's just a physical fact, it means we're going to have to be making decisions about priorities and how we can get the most well-being per joule kind of idea. How can we get the most well-being and very basic needs from whatever energy resources are going to be locally available? Because I think a lot of this is also going to have to be a transition to much more localized and community-owned and operated energy systems.
Yeah, and again, I suppose, bringing it back to agriculture, it's far better to use your litre of diesel fuel in your tractor. You'll get far more bang for buck doing that than using that diesel to, I don't know, ship plastic junk around the country.
Right.
Yeah, it's a much better utilization of that precious resource.
Yeah. So another question here about the role of movements like regenerative agriculture and urban farming, and whether there's any information about net energy analyses of these sorts of agricultural approaches.
As far as I know, there isn't any net energy analysis of those systems, but intuitively, it kind of feels, because their focus is on reducing inputs, intuitively, it feels like their energy consumption would go down, would be less than a conventional system. And the same is true for emissions as well. They're likely to go down. But again, nobody's done any, as far as I know, and I haven't done an exhaustive search, but as far as I know, nobody's done that comparison to see if you transferred yourself to a regenerative agricultural system, then you had lower emissions. But it feels like it should, intuitively speaking to me, just because of the way they're operating their systems. It might actually be a good place to show that short video, Jack, that I was talking about, because that's about a regenerative system.
How long is that, Craig?
It is under 10 minutes. It's about 8 minutes, I think.
Mm-hmm. Okay, I'd just like to make a comment about the idea of regenerative or urban agriculture, and that is, it implies a lot more human labor.
Yep, but again,
and we are actually, as we were discussing a little earlier, very energy efficient.
Yep.
And prior to the fossil fuel era in the beginning of the 20th century, when it really started to escalate, most energy in society was provided by human labor.
Yep.
And animal labor. And I suggest that we're going to have to be thinking about going back to that.
Yep. Well, if we contract our economies, then there's going to be a lot of people that don't have much to do. So they should probably deploy
Yeah.
themselves in growing food.
Yeah. Just before we go to your video, there's one more question here. It's wondering about the spatial planning implications of operating in a low EORI future. I think of rural village layouts in parts of Asia with tracks radiating out to farm plots within walking distance and bullocks plowing and transporting. What EORI system might that have? And might permaculture help?
I would imagine permaculture most definitely would help. But the mindset of permaculture is that everything that you do has to have multiple uses, right? So yeah, you're getting a lot more bang for buck. And yeah, I sort of envisage that we will probably have more rural living in the future, unlike our futurist friends who think we're going to be living in these beautiful modern cities all over the world. Yeah, I think there's going to be a drift back to the country, a forced drift back to the country. There's just no way cities will be sustainable as they are currently. Yeah, it's hard to imagine what that transition is going to be, but I don't get the impression that it's going to be a pretty transition. I think there's going to be a lot of gnashing of teeth.
Yes, I mean, just
until people realize that, well, actually, we've got to go this way.
Yeah, a little bit of data about energy use in urban areas. My understanding is that a third of the energy that municipalities use is used simply to transport fresh water in and dirty water out.
Wow.
A full third of municipal energy use.
Yeah.
That gives you an indication of what we're going to be up against.
Yeah, that's crazy, eh?
Yeah. Yeah, let's see your video.
Yeah, I just stumbled upon this other slide that I had put in there, which is coming from Project Drawdown. I don't know if you're aware of, probably you're aware of Project Drawdown.
A great project, yes.
Yeah, so the solutions, I've highlighted some solutions there in red that are applicable to New Zealand agriculture and agricultural landscapes. Well, aside from the reduced food waste and plant-rich diet, but we could be transforming our agricultural landscapes into silver pasture, regen ag, utilizing conservation agriculture, tree intercropping, better managed grazing. A lot of these things actually come in under regenerative agriculture or agroecology. Farmland restoration, so we've got a lot of sub-quality land that we could improve, and multi-strata agroforestry could also get in there. And the ones that I've highlighted in blue there are the only areas that my research group are researching in New Zealand. So nutrient management and farmland irrigation. That's where all the agricultural investment in plant and food research is going in terms of these solutions that are applicable to New Zealand, these drawdown solutions that are applicable to our agricultural landscapes. So we're missing the boat. There's a huge number of things that we should be looking into and should be transferring to. But anyway,
yeah. One of the interesting things about the drawdown compendium of solutions is that these are all solutions that currently exist. We don't have to wait for their development. We can apply these now. Yeah.
So this, hopefully the slides change. This is an example of regenerative agriculture. So this is a couple, Mark and Jen Shepherd, and they call their farm New Forest Farm. So this is in Southwest Wisconsin. This is soy and corn growing area. And they looked at their, I think it was more Mark looked across the boundary into his neighbor's fields and sort of said to himself, there's something wrong with this picture. How can we do this better? And he went down this journey of regen ag, basically, or permaculture on a large scale. So he designed his farm in and around water. So if you look at the picture on the right, that's where the water flows go on his farm. So it's very topographically based, and he's got water collection areas and water dams, if you like. Plant a lot of trees, and you can see that they're all following contour there. And all that is designed to capture and store water on his farm in order to improve its productivity, and for him not to have to use irrigation. And the energy, and consequently his energy demand is very, very low, because he's not pumping water. So they've got a little video here, which is on, you can find it on YouTube, but this is Mark talking about his farm and what we could be doing in our agricultural landscapes.
Hi there, my name's Mark Shepard. We're at New Forest
Can you hear
Farm
the
in
audio?
Southwest Wisconsin. For the
Yes.
past 23 years, we've been converting a typical corn and beans row crops farm into a perennial polyculture agroforestry system that mimics the oak savanna plant community type. Our primary cash flow has been produce, nursery stock, especially chestnuts and hazels. My edible woody crops nursery, Forest Agriculture Enterprises, has been selling chestnut, hazelnut, pine nut, apples, a whole number of different edible crops, and we're doing the breeding right here on the farm. We also raise grass-fed livestock, beef and pork. Part of where we're standing right now is in an alley cropping system. Our first job on the farm was to install a water management system. What we did is way up at the valley, up this alley that way, there's a small pond. When that fills full of rainwater in a storm, we have channels that are excavated to bring it out to the ridge. All of the water that would have gone to this valley now hits these channels and spreads to the ridge. But you can see here by the shape of this alley that the water would flow from way up in the head of the valley, slightly downhill. In this case, we're using a 1% slope. That means it drops 1 foot over every 100 foot that it moves forward. So it comes out this way to the ridge. That valley form brings the water this way. Once it hits the ridge, it hits this big level spot that's a slight depression, and there's a rim here, and it becomes a big shallow pond, and it sheets over the edge of the pond up on the ridge. So formerly, the valleys were the wettest spots on the farm. Now the ridges have wet spots on them, which is fine by me because I know this water is soaking in deep. And who's benefiting from the water being soaked in deep are all of the chestnut trees up on this ridge, for example. The asparagus gets it as well. And of course, everything is alley cropped. This happens to be alley cropped with chestnuts. Hybrid chestnuts, they're Chinese-European crosses. The Chinese chestnuts have typically not been cold hardy enough here in Southwest Wisconsin. As I keep bringing more genetics onto the site, it seems that my hybrids are appearing to be more and more Chinese. My original thought was we would take the cold hardiness of the American chestnut and the blight resistance of the Chinese chestnut. When we cross them, we'll have a cold hardy blight resistant. The ones that die from the blight, we know they're not resistant, and that's okay, let them die. Then the ones that freeze to the ground, we know that they're not cold hardy, and that's fine. The survivors that we've treated with strategic total utter neglect, stun, the survivors are the ones that are suited for this site. And then of course we select for the ones that reproduce really young in their lives, and then the ones that produce the heaviest crops. So this is alley cropping with an annual crop. If you'd like to see alley cropping with a perennial crop, we can walk right over here this way. All right, here we are in one of the alleys where we're growing asparagus as the cash crop. In the alley, we have 4 such alleys. Chestnut is on either side. Approximately 2 acres of asparagus, so that's 2 football fields worth of asparagus. What's interesting about the asparagus, because of the competitive effects, we grow it in a heavy sod just like the asparagus you see in the ditch on the side of the road, and it's growing in competition with the chestnut trees right nearby. We probably get about half the yields that you could expect out of a clean tilled asparagus crop, but that's not my goals. My goals are to have an easy system to manage that is profitable by itself. So once you plant the asparagus, take minimal care of it. I mow it a few times in the springtime, scalp mow it right to the ground, and then the asparagus itself emerges through the weeds, which are mostly grasses. We see some, various different ragweeds and stuff like that. It's a 22-year-old patch now, 23 years old. Meanwhile, though, as the asparagus has peaked in production. The chestnuts have started to increase in production. And now as the asparagus starts to decline, the chestnut yields are increasing even more. And I don't know if we're going to do the asparagus for another 2 years, 5 years, 10 years, mow it and have it all be pasture and graze cattle in here. I've got options. When you're doing an alley cropping system, you end up with options. The hazelnuts that we're growing here at New Forest Farm are all hybrid, which means that they're different species mixed together. We've got European American, we have beaked, which is also a Native American type. The two plants have dramatically different growth characteristics. The American hazel is a rounded shrub form. Both European and American are multi-stem. The American hazel classically has a husk around the nut that encloses the whole nut. On the more American type hybrid hazels that are being grown in upper Midwest, the idea is to grow them high density within the row, approaching 1,000 stems per acre, and then have them grown as hedgerows and have them be harvested over the top with a straddle harvester. Currently right now, the Americans are really easy to harvest by hand because the plant doesn't really get much taller than 8 or 10 foot tall. The stems are really flexible and they don't break. You just bend them down to the ground, you strip the nuts off. They get dried down and then they have to be husked. The husk has to be removed mechanically. We use a modified version of the insides of a combine to do that. So these are hazelnuts that we in the northern climates that get 20 below, 40 below, we can grow, and we can grow them either like European small trees, or we can grow the American type with the enclosed husk and either harvest them by hand or over the top with a straddle harvester. So we're in the some of the oldest chestnut trees on New Forest Farm in southwest Wisconsin. And this is an area that we use exclusively as a silvopasture system, most specifically for pigs. They get a mixed feed ration, organic feed ration, mostly for the vitamin part of it, the minerals, so they get a good balanced mineral. I only feed them enough to feed a little 30-pound pig. So if they want to eat more and if they're hungry, they have to go out and graze more. They clean it completely out. So whatever's in season, starting with currants in the spring, raspberries, underneath the currants, they'll get rid of all of the weeds underneath the currants and they'll eat the berries right off the bush. Then they'll kind of move to the raspberries, then they move to the mulberries. This time of year, they're kind of between. They just went through mulberries and cherries. They're just finishing up cherries. There's still some mulberries on the trees. They've started tearing into the grapes. They'll pull the vines right off of the trees. I let the grapes climb low on the trees. I don't let them climb all the way up high. I pull the vines down if the pigs don't. The pigs will pull the vines down, eat all the leaves off the vine. They'll eat the fruit. They'll be crunching on big bunches of green grapes. They'll go up to elderberries as the elderberries start to get ripe, and they'll eat the elderberries right off the tree. They'll get up to full body size by mid-September when the chestnuts start to ripen, and then they just fatten up because the chestnut it's a high carbohydrate. It's a lot like eating corn, and they just gorge on chestnuts and they turn into nice chestnut fattened hogs. And the last month of their life, I'll feed them their morning snack and their evening snack on the livestock trailer. So when the day comes to go to the slaughterhouse, I just go up to the trailer and shut the door. No stress of forcing them down a squeeze chute or using cattle prods to get them to load a trailer. They just do it all by themselves. We named every single one of them. They're all identifiable. They all get patted every single day. They get treated really well. We care for them as pets. I don't ever want this to be a callous, heartless thing. I think that's part of our humanity, is the fact that we do identify with these animals. These are our friends and they will become us. I'm gonna have pork chops tonight, I really am. I know that they've lived a good, healthy, happy life and they only have one bad day. Oh, here we go. Yes, my boy. Good old pig.
So there you go.
Yeah, it's a great example of someone who's connected to a piece of land and who understands the strengths and weaknesses of that particular land and how to manage the natural processes,
Exactly.
rather than trying to impose a industrial model on it.
But it does give you some hope that there's people out there that are doing amazing things. It can be done. I've actually got that guy's book, and he's done a calculation of the number of calories or the amount of produce and that's coming off his land. He's far more productive over his entire farm than his neighbors, but for individual crops, his productivity is lower. But that's usually the argument that's made. It's like, oh, conventional agriculture has higher yields. It's like, yes, that's true, but when you have a three-dimensional system like that, he's got massive production. All those nuts and things, it's just, yeah, phenomenal production.
Yeah, no, it's a lovely example. Yeah, I mean, it also speaks to the issue of corporatized farming, which is really profit-driven, and the uniformity that requires, at least in their minds.
Yeah, and that digital agriculture example that I gave during the talk is a further advancement of that industrialization, and
yes.
it's it's not a good direction. It has no ecological. There's no consideration of ecology or biology in there. It's a very much inputs in and outputs out model.
Yeah, and I was really taken by the low net energy produced by fisheries and aquaponics.
Yep.
I had assumed that it was much higher.
Yeah.
So
again, we have in New Zealand, we've got a massive investment within PFR. Actually, the government's given us an awful lot of money for offshore aquaculture. So we have all these environmental situations starting to occur with our inshore aquaculture system. So basically, too much fish food is coming out of the system and polluting our coastal waterways. So the solution is, well, why don't we put that offshore? And we have a much bigger area there. Dilution is the solution to pollution, among other things. I'm being a bit facetious there, but again, in my head, I'm like, well, okay, now you've got to either travel out there and look after these fish, or you need to have a highly automated system in a very harsh and violent environment, which is the open ocean. And it's just nonsensical to me. Again, it's just huge amounts of energy going into that and resource for what? The so-called blue economy. And it's like, well, surely we can do that better.
Yeah. Well, I mean, the good news about those sort of things is that there's some understanding that things have to change. They're just changing in the wrong way.
Yeah.
But if we can keep pointing out some of these difficulties and limitations, hopefully, we can steer the decisions and the investment toward, the more regenerative and constructive outcomes.
Yeah. So that's a very politically hot potato. There is quite a lot of pushback within the regen space from scientists who have spent their whole careers looking at soil chemistry and soil physics and things like that, and they basically say, regenerative agriculture can't happen. It's mining the soil, and we've done all this research. We already know that we've got really efficient systems in New Zealand, and blah blah blah. Anyway, they're really against it, and then you have the practitioners on the other end who are just trying things out at this point. There's some people that are more further down the track than others. And yeah, there's this real dichotomy of well, it's basically being painted as believers and non-believers. That regenerative agriculture is a religion, essentially, and it's going to ruin our farming systems. And you've got to feel sorry for, so there's a recent white paper put out by Landcare, and the scientist who was mainly spearheading that has just been hammered with totally unproductive and unwarranted criticism and even character assassination. It's just like, can we have a sensible adult conversation about this? It's maddening. It really is.
Craig, what was the land care report? It sounds like it was an interesting and important thing that we should know.
So if you go to Our Land and Water, which is one of the national science challenges that...
Sorry, say again, please.
Our Land and Water. So it's one of the national science challenges that the National Party brought in.
Mm-hmm.
So there's 10 challenges there, and actually you should be able to just do a search on their webpage for regenerative agriculture. It'll come up. Let me see if I can find it. Yeah, so if you go to, can you still see my screen?
Yes.
Yeah, so you can see the second link down there. Regenerative agriculture white paper sets out pressing whatever the other words there are.
The second one, okay, regenerative ag white
pressing
paper.
research priorities. So that's what they focused on. They basically bought about, I think Gwen had maybe up to 400 people contributing to this. So that's everyone from consultants to farmers to economists to scientists, a whole range of people put their views into this. And so this white paper is a summary of that. It's put together a little bit rushed, so it's doesn't read as well as it could, but there's a whole bunch of follow-up, smaller chunks of the report that will come out piece by piece. So the actual report is something like 400 pages long. This white paper is about 70 pages long, and it's reasonably accessible, but it's basically sort of saying, okay, in the New Zealand context, what could regenerative agriculture look like? And how might we get there? And what is the research that we need to do in order to quell people's fears about these big changes that we might be putting into our agricultural systems? So it's actually quite good, but like I say, there's a group of let's just call them old school scientists who have a lot of experience. You can't knock them for that, but they're just not open-minded enough to sort of see things in a different way, which is frustrating.
Yeah, well, thanks for bringing our attention to it. It looks like a very interesting paper.
MPI is very interested in the idea of regen ag, and they are actually putting up some funding for people to do research in that space. So up until now, we haven't had any money to do anything remotely close to agroecology. There's a little bit that's happened in the universities, and say the likes of Steve Ratton, who unfortunately died recently, would be a perfect example of a researcher that was doing research in agroecology. But yeah, very little work done in New Zealand in this space. It's mostly South America and a little bit in Europe and things like that. But most of the Western nations haven't really jumped onto this agroecology bandwagon yet to really get some good research and understanding of our context-specific environments. Right.
Craig, there's one last question here. Well, there's actually two now, but one question is, what did you tell the Climate Commission? What was your feedback?
My feedback was very politically distilled to something that I hoped would be a little bit more palatable, and basically said we need to rethink our agricultural systems, and there's plenty of ways that we already know of how to do that. We need to promote those directions and try and move forward. So actually Dugald is probably online here, is he?
Yes.
So yeah, so I've contributed to the Wise Responses response to the Climate Change Commission, and yeah, there's probably a paragraph in there from me that basically says we need to pull our heads in and have a real serious think about how we can get away from our very industrialized agricultural mindset and be a bit more ecological.
Yeah.
But
Good.
it'll probably fall on deaf ears. I actually have no faith in policy, to be fair at this point.
Well, I think it just bears repeating and repeating and repeating. So don't
Yeah.
give up. And there's one final question here. It is from Dougal, and that is: do you see a role for soil microbiology in contributing to the EROI dilemma?
Absolutely. So again, from my own research experience, I've been at Plant and Food now for 10 years and have done very little of what I would call meaningful research in properly understanding and providing answers for farmers on these agroecological problems. So if a farmer came to me and said, what are my soil microbes contributing to my farm productivity, I wouldn't be able to tell them. I wouldn't be able to give them an answer. I'd be able to give them a bit of a fluffy answer. But because I haven't actually got any, had any chance to do some proper research, I would struggle to answer that question. But say, for example, in fertilizer, we know that we have rhizobacteria. So they sit in nodules on plants like clover, for example, and fix nitrogen for the plant and for the localized environment around them. But there's also this huge ream of bacteria that can do that without being associated with the plant. So these are called free-living nitrogen fixers. How do we encourage those bacteria to do their job better, and so we can cut fertilizer use? We might be able to even remove fertilizer completely if we can really ramp up the activity of those particular bacteria. And it could be as simple as what the regenerative agriculture people promote, which is to have a massive plant diversity, which then feeds in a much wider diversity of organic carbon, liquid carbon into the soil. Those microbes then respond to those carbon sources. And when you're building biomass, you're also needing nitrogen. So they'll be fixing nitrogen and delivering organic nitrogen into the system instead of mineral nitrogen. So when I'm talking organic nitrogen, I'm talking organic molecules that contain nitrogen, which bacteria then break up and release the nitrogen for the plant, versus mineral nitrogen, which is stuff that we add in the bag. So that's ammonia and nitrate predominantly, or urea would be another example of a mineral nitrogen source where we're basically creating it and putting it on the paddock. So we've circumvented that whole cycle by adding fertilizer. So yeah, microbiology could have a massive role to play in that EROI dilemma, because we can harness the biology to do a whole bunch of the work for us.
I suppose the first thing is simply to recognize that the bacteria are the real farmers. Absolutely,
yeah. And again, if you listen to some of these permaculture people, regen people, they're basically saying we're farming soil. We're not farming produce as such. We're building soil. That's our contribution.
That's what it's all about. That's right.
Yeah. Exactly.
Craig, we reached the end, and thank you very much for a terrific presentation and presenting large numbers of big issues that we really need to be thinking about, and that some of us already are. So it's good to know that there's more of us out there, and keep at it. It's basically needed, and we hope to put this presentation up on YouTube in the next few days. And just to let everyone know that the May presentation for the webinar series will focus on the whole issue of intergenerational strategies. You know, how do we how do we stop discounting the future so greatly and take into account, you know, the kind of long-term thinking that as Craig has indicated we need to do, and how do we put that into policies in a broader level, because there's so many areas in which we need to take that long-term perspective. It'll be Jonathan Boston from Victoria U that will be presenting. So hope you all can join us then and tell others about it as well. So Craig, thanks again. We'll sign off for now, and hopefully our paths will cross again.
Yeah, hopefully. And yeah, we'll try and get some of this information out.
Right. Okay.
All right.
Take care.
Good night.
Bye-bye.
Good night.